let's continue from where I left last time. If anybody needs to grab power strips, I did bring them. So last time we're calculating Unisim directly gives us H molar, S molar, V molar, and we're calculating A, U, and J. And to my embarrassment, I wasn't sure about the multiplication factors, and I should have left it on, whether I should multiply by 1,000 to change the pressure to Pascal. The final answer is no, we shouldn't multiply by 1,000, because what we have on the others is not joules, it's kilojoules per kilogram mole. So we need to have the units kilojoules per kilogram mole. So we're getting U as H minus PV. This guy is kilojoules per kilogram mole. V is cubic meters per kilogram mole. If I have P in pascals, Pascal times meter cube is joule. So if I convert it to Pascal, which is what I did when I multiplied by 1,000, if I converted kilopascals to pascals, I would have PV as joules per kilogram mole instead of kilojoules per kilogram mole. Clear? Everything else is given as kilojoules per kilogram mole. So you have to have consistent units, it has to be kilojoules per kilogram mole. So if I multiply the pressure by 1,000 to change it to pascals, I would have as a result PV as joules per kilogram mole. With me? But I need to have kilojoules per kilogram mole. So what is that? If you have pressure with kilopascals, yeah, better way of explaining, okay? Need kilojoules per kilogram mole. That's the best way to explain it. P pascals times V cubic meters per kilogram mole gives joules per kilogram mole. On the other hand, if I leave P as kilopascals times V cubic meters per kilogram mole, I will get joules times 1,000, which is kilojoules. That gives kilojoules per kilogram mole. So the answer is that I shouldn't have multiplied by 1,000. So let's go back and fix this. I had put times 1,000. So we need to remove the times 1,000, which makes the numbers that make a lot more sense. So first we had U. So U is B3, which is H, minus B1, and I multiply times 1,000, which is the pressure, times temperature, times volume, which is B5. So we need to remove the times 1,000. So remove the times 1,000. So that's the correct U. Now that makes a lot more sense. And let's see what else we have to fix. So this G is fine. This is U minus T times S. So that's correct.
What is that?
What do you mean, what's that?
You don't have a unit for
It's also Gibbs.
It's also Gibbs. It's the other way. We calculate G, Gibbs two ways. So this needs to be fixed. It has the 1,000. That has to be removed, and then we'll get the same answer. And I think A is correct. I don't think we can fix anything.
They're off by a lot.
That's where we are. Oh, hold it. They're not the same. Hold it. They should be the same. What I do. Okay. So now U is correct. Okay, let me check A. So A, I have B7, which is now the correct U, minus T, which is correct, times B4, S is correct. So that's correct. And this is calculated as A plus B. B, that's correct. Second?
Is there any way to make it bigger?
No, no, unfortunately, there's no way I can make the unison print bigger. Yes, Dan?
Last one, actually, how do
Louder.
you pull up the spreadsheet? I didn't catch
How to
that.
pull up the spreadsheet,
Ah. You get the spreadsheet by clicking right here. See what the arrow is?
Okay.
And bringing it somewhere.
What's that other G you have there?
That's the alternative calculation. Let's see what I'm not getting
Second.
the same. Should be getting the same thing. You can get G two ways calculated. Let's see what I do. You get the same. Let's see. 273.15. That's correct. You got 273.15. Yes. Wait a minute, that's an A. That's the same as A, but what did I miss before? Is that the same as A, that's with A twice? Oh, that's my problem, okay. Okay. So, again, calculations. First of all, U. What is U? Is B3, which is H, minus B1, which is pressure in kilopascals, times B5, which is volume in cubic meters per kilogram mole. Okay? A is what? Is one way you can get A is U minus TS. Actually, that's how we get it. U minus TS. So U minus temperature, which is in Kelvin, B2 plus 273.15 times the enthalpy, which is the B4. G is what? G is A plus PV. That's one way to get G. The other way to get it is H minus TS. So here, instead of putting H, I have B7 should have been H. Should be B3 minus that. So another, that should be B3. And now I should get the same answer. Yeah, there we go. So, yeah, let me write it down. So we got U. Okay, we got A as U minus TS. We got G two ways. It's A plus or is H okay?
I got everything right except for the first G. Can you go back?
Well, the first is A plus PV.
Yeah.
So here it is.
So I accidentally have minus.
A is B6 plus B1P.
Yep.
So we didn't need to use any conversion. So everybody clear? Any questions? Okay, so you understand why the 1,000 didn't belong? Because it's kilojoules. Okay? All right. Simple. All right. So my objective is to, first of all, finish everything so you can do your homework. So I can assign the homework, assign a date for it. The next thing, for every substance, unit symmetric component gives the coefficients as a function of temperature of the mass, ideal gas, enthalpy. So here we have nitrogen. So if you go to the beaker, okay, go to the beaker, go to components, go to component list, and click view. For every component, for example, click nitrogen, if you double click it, you have several properties. For example, on the critical, you will see the critical temperature, pressure, and volume, the eccentric factor, about which we're going to be talking later in class, and also things like the molecular weight. Then on temperature dependence, you see here the ideal gas enthalpy. And you can see the form that it has. It gives an expression as a polynomial with several coefficients. It turns out that something is not correct here. Something does not agree with what Unisim is using internally. If you use this expression to calculate an enthalpy, an ideal gas enthalpy, use ideal gas law, so you have ideal gas, and use this expression to calculate enthalpy. You're not going to get the same answer as Unisim gives you. There's somewhere an internal error. So your homework, first problem, and second problem, actually first problem ABC, is a little bit detective work to figure out what is wrong here. I won't give you the answer, but I'm giving you some guidance. I will tell you this much. One of those parameters that are given here is incorrect. So here you can see after f everything becomes 0. So it's a polynomial expression until the f term. One of those values is incorrect. And if you do the homework, you should be able to figure out which one is incorrect. Specifically, problem 1b tells you to write an expression for h hat as a function of temperature. So we're talking about this particular expression here that you're saying, what it gives you, which is this, this, and you can see the expression would be h hat equals, in this case for nitrogen, 2 points. So for nitrogen we would have,
What does Y stand for?
what you're calculating, h hat. Why is the h hat? So you would have, what this tells you is that h hat equals 2 points for nitrogen, right? This is for nitrogen. 2.863 plus the next coefficient is 6 times. So plus 0.982, I will not write the rest, 0.982 t, plus the next term is 9.71 times 10 to the minus 5 t squared, and so on. Okay? That's what this suggests. So that's what I'm asking, to write this expression. Okay? So after you have written this expression, this is h hat. Okay? And I'm asking you to calculate with this expression h hat at t reference. We already did the t reference for nitrogen where it was 0. Do you remember where h hat for nitrogen was 0? What temperature it was 0?
25 C.
25 degrees C. So if you put this at 25 degrees C, translated to Kelvin, you are not going to get 0. So something is wrong. Because you know H should be, Unisim uses 0, yet that expression with those parameters is not 0. Okay? So, from H hat, you can get an expression for Cp hat at any temperature. Who will tell me if I have H hat as a function of temperature,
You just integrate it.
what is Cp hat as a function of temperature?
The derivative of H hat with respect to
The
temperature.
derivative, exactly. D Cp hat dt.
DH.
dH hat. So, differentiate above, you'll get, for example, 0.982 plus 2 times 9.71 times 10 to the minus 5 t plus and so on. Okay, you can differentiate the above expression and get the expression of Cp hat as a function of temperature. Then, if I have Cp hat at any temperature, I can calculate from that H at any reference, at any temperature. So we now take this Cp hat expression and use the fact that at T reference, what should H be? 0 for at least the species have zero heat of formation. So how would I get H at any temperature? Okay, I'll ask,
My guess would be
what's the relationship? I have now Cp hat. How do I get H? Integrate, right? So that's the integral from T reference. It's ideal gas, so it's only temperature dependent, no pressure dependent. Okay? So you can integrate this expression, okay, and get H hat from this expression. And then I'm asking you to calculate, using that expression by hand, what is the enthalpy, what is H hat at T reference, which of course you know what it should be, and then at 300 and at 700 degrees. And then use unison to see what is H hat at the T reference, 300 and 700, and see if it agrees.
When you say use unison, do you mean use the unison value for H?
No, use actually unison. Make it unison stream
Okay.
and have it show what is your H hat.
Okay.
Yes?
Why do you have to, why can't you just plug in the temperature that you want to find H at? Why do you have to integrate?
I'm going, first of all, you already did this, right? You did this, and you didn't get the right answer. Okay? So I'm guiding you to figure out what is wrong in that expression. You find out that perhaps with this integrated expression, you get the correct H hat. At least agrees with what unison is giving you internally. This expression did not. It's kind of obvious now. I almost told you what is incorrect here, but I want you to do the thinking and figure out what is incorrect. Okay?
For the first term. This is the first term.
Be quiet. All right. So it's a little technical work. I want you to go through that. Okay? Yes, it's not difficult, but in case it was confusing, that's what else. Okay? So basically here we're using what the reference is. All right? All right. And then, so that should allow you to do problem 1. And problem 2 is a mixing problem that we're moving now to that right away. Okay? So clear about what's needed to be done in the homework? Okay? Jessica, questions? You sure? Anybody else? Let me see.